Just a quick blurb here. Here's our quiz. We have a vector and a set of 3 vectors. We want to determine whether this vector is in the span of this set. Okay? And it's natural, and everybody did it one way or the other, to write a system matrix equation. Okay? Multiple of this plus a multiple of this plus a multiple of this equals this, and everybody did quite well with that. Okay? And then some people wrote a matrix equation, and some people chose to do the augmented matrix. It's the same thing. Okay? And some people are actually reducing the augmented matrix. It's not necessary to reduce the augmented matrix in order to answer the question. It's a much quicker and easier way to do it. Okay, so I'm just going to say not necessarily to reduce, it's not necessary to reduce the matrix to answer this question. So I'm going to give you a few minutes to think about what you might be able to do other than reducing the matrix. Okay? Now there's a very high probability if this matrix will reduce to the identity, you'll be able to reduce the 3x3 matrix to the identity, so the augmented matrix and ensure a solution. And you would be able to find out what the solution is. But notice, I didn't ask you to find a linear combination. I didn't ask you to find the constants you need to get this vector, right? Okay. So there's a simple test, much easier than reducing a matrix. Okay, now, and also usually in the linear algebra class at this stage, people still have trouble reducing matrices. You don't have any trouble, okay? Which is good. It means you're well prepared for this course, okay? Now, we'll see how well prepared you are for everything comes at you, but you're going to do okay. Keep working the way you're working. Okay, so I can say that just writing it out quickly. Actually, I don't even want to write out the numbers. I don't really care about the numbers. You can deal with the numbers. You don't have any trouble dealing with the numbers. Not that you never make a mistake. I do too. Okay. So, but your equation will be C1B1 plus C2B2 plus C3B3 equals this, right? So let's just insert comment. We're going to call this our vector B. Okay. And here's B1. B2. And B3. So the system of equations is, well, linear combination could be written. You don't have to use C for the constant, but that's what everybody in the world uses, as far as I know. Well, not everybody in the world, maybe. Okay, it's C1 and I'm writing the matrix before I write out the equations. And you've got C1 times this plus C2 times A, B, C matrix vector plus C3 times negative B, B, L. Okay. Of course, that's C1, B1, C2, B2, plus C3, B3. And that has to equal your B vector. Well, first of all, C1, B1 plus C2, B2 plus C3, B3 is just your matrix here times the vector C1, C2, C3. Okay. So we write this as C1, C2, C3. C1, C2, C3. And that should be familiar notation. Your book has done it, you've read it. And if not, you certainly understand that B1 is just this column, B2 is this column, B3 is this column. So right there it is, right? Okay, so in this case, B is vector A, B, negative C. Now you could solve this by writing the augmented matrix. You could take the matrix D1, D2, B3, D and reduce it. Alternatively, we could reduce B1, B2, B3. C. Either way, you get a solution as long as the B1, B2, B3 matrix, which is here or here, reduces to the identity. Okay. So the solution is guaranteed. Either way, depending whether you do the matrix equation or the augmented matrix, which are equivalent. With the matrix B1, B2, B3. Get tired of writing that, so I'm going to call it A. Reduces to the identity by reduces. Gaussian reduction. Forgot to throw it on. Reduction with that. Okay. Makes sense. Now, what's a simple test for whether this matrix reduces to the identity? You don't have to reduce it. Matrix reduces to the identity if and only if the determinant of A is not equal to 0. That's a much easier way to answer the questions that I posed. Now, it is possible that your matrix would reduce to a matrix with a row of zeros. In that case, it's still possible that your B vector could be a linear combination. Okay. If, let's say, one of the vectors is linearly dependent on the others, and of course that's going to be the case if the matrix does have determinant 0. It's still possible that B is in the span of that two-dimensional subspace or one-dimensional subspace, as the case may be. So B could actually be a multiple of one of these vectors. Okay. Then it wouldn't matter that the other two vectors are also multiples of this vector. You would still have a solution. So you have to think through those possibilities. But what I want to focus on right now is this possibility. Okay, so the one thing that I hoped to see, but I wasn't all that optimistic because you're still putting things together, is the determinant will tell you there's very high probability that with the A, B, and C, E, F, G letters are numbers that you have, which are in some sense not really random, but fairly close to what you get if you randomly generated a matrix. Okay, with numbers between say 1 and 2. There's very high probability that the determinant of that matrix won't be 0. Okay, determinant is not, the matrix will be not singular. Okay. Singular means the unusual case, which is that the determinant is 0. You randomly generate a matrix with integers in some range. The bigger your set of integers, the less the probability that you're going to get a determinant of 0. And you might ponder that statement. Okay, so the matrix A reduces if and only if this. So you could have easily tested. Okay, assuming well, if the determinant of A is not 0, then A is invertible. Obviously, if it reduces to the identity, you augment it with the identity and reduce that, you're going to get the inverse matrix. So that we have this solution. Make sense? Well, then we can say the answer to every question that I put. If I'm taking the determinant of a matrix, you can tell me that, yeah, it doesn't really matter what this is. This matrix reduces to the identity, so it can be inverted. Or in the augmented matrix, you know, your first 3 columns will reduce to the identity, so you will get a solution. Also, we just proved that every vector in the span, or every vector in our trees in the span of the set, it didn't matter what this vector was. We just showed that it's true no matter what B is. It doesn't have to be your specific. So you could actually have shown this and then said, well, this is just a simple instance of this. Understand how we're developing a little bit of structure and putting these things together. Okay. Then what about this one? Well, in the case of your matrix, it's very likely that your matrix has a determinant that's not zero. So AX equals 0 is going to have a unique solution, right? And well, that's an important case. So let's talk a little bit more about that. But clearly, if your matrix has non-zero determinant, the answer to these questions are yes, yes, and yes. Okay? So if the determinant of A is 0, then you can make a very quick argument. Okay? Now, as I say, what I saw was that everybody set up the equations, either the augmented matrix or the matrix equation correctly, and that makes me happy. Okay? I've been ecstatic if people have done this, but I wasn't really expecting it, even though y'all are smart enough to do it. You haven't done enough problems to have sorted all this out. Okay? But it's conceivable, certainly conceivable, and it better be conceivable in the near future. You understand how the determinant allows you to test this. Okay, well, the other, and of course, this is true because the matrix would be invertible, so it actually be the inverse matrix times the zero vector, which is going to be the zero vector. Okay. I'll also mention the connection with the augmented matrix. Okay. That's it. Determinant's not zero. You can write this out, and that would be a 3-line complete rigorous answer to the question. The augmented matrix, we're just taking a quick look at the augmented matrix. And you're going to want to think about this, I think it's not completely obvious to you. Okay. A reduces to I, assuming the determinant is non-zero. Now, your column of zeros doesn't change because whatever multiples of what row you're adding to what other row, you're just adding multiples of 0 to multiples of 0. Okay. So that the right-hand column and this is an important idea. It relates to what we call the kernel of the vector space of the null space. This is a preliminary. The null space is a set of all solutions of this equation. The vector is invertible, and the null space consists only of the zero vector. Now, of course, I could have given you a set of 2 vectors here and asked, is this a linear combination of these 2 vectors? In all likelihood, the answer would be no. It'd be easy to reduce that equation. You know, just 2 lines, but you do that by hand. Of course, machinery will do it for you too. So sometimes you do need to reduce the matrix. In this case, the matrix would be square. So that either this or this leads you to the same conclusion. Okay. Okay, well, try to sort that out. Now, let me pause for a second. There are a lot of places I could go from this. I want to go in the order of the text. And since I didn't know how you're going to answer the question, my only plan was make sure we understand this, and then let's look what the text is going to tell you. Okay? So let me take a quick look, and I should have opened the text, but I didn't. Okay. Basis is a set of linearly independent vectors spanning V. Well, what we have just done with these problems is prove that if you have a set of 3 vectors in R3, it gives you a matrix of the columns whose determinant is not 0, and these vectors are linearly independent. Okay. Because, among other things, none of the vectors can be a multiple of any of the others. And also, any vector in the space can be expressed as a linear combination of these 3 vectors. Okay? So these 3 vectors span R3, unless lightning struck and you happen to have numbers to be determinant of A was 0. Okay? Very unlikely it did, but we have to keep that in mind. Okay? So a basis is very, very interesting. Now I'd like to do a lot of proofs here, but you're going to have to read them. You should understand why some of these things are true. Okay. So I'm going to say, I don't want to say this. Well, number of vectors in the basis of a given vector space is the same for any basis. Pretty easy to prove that. This number is what we call the dimension of V. Our example. We have a set of 3 linearly independent vectors and R3. So the dimension R3 is 3. Three-dimensional space. We're kind of used to that terminology, but you all know we're moving around in three-dimensional space. Dimension of R4 will be 4. We need 4 linearly independent vectors to span R4. Okay, well, let's look at examples of bases, which is the plural of bases. Okay. Standard bases, or bases. That's not the word pronounced. Okay, standard bases. The simplest basis is a basis with a lot of ones in it. Okay. That's the simplest basis. That's your standard basis for R3. Okay, so P2, and what P2 is space of polynomials of degree 2. Actually, to be degree 2 or less, because the coefficient of x squared or of x or a constant number, as we've seen, could be 0, in which gives you lower dimensional subspace. Okay, but there's your standard basis. Okay. The typical vector is a times x squared plus b times x plus c times 1, a linear combination of these three. So what's the dimension of this space? Show me with your fingers. What's the dimension of P2? How many vectors do we have in this basis? Okay, get that straight, because you see the 2, you want to think it's dimension. No. Because you have a dimension 0 here. You know, it's a degree 0, degree 1, and degree 2. Okay. I have shown that that's linearly independent. You can deal with that. But none of these can be expressed as a linear combination of the other 2. You can't write x as a linear combination of x squared and 1. Okay? You can't write 1 as a linear combination of x and x squared. That would mean that 1 has to equal some multiple of x plus a multiple of x squared for all possible values of x. And that equation would have no solution. There might be solutions, okay? X squared plus x equals 1 is equivalent to x squared plus x minus 1 equals 0. The quadratic formula will give you a solution. But that's only one value of x. That would be true for all values of x. You might want to ponder that statement. Okay, well, anyhow, there we have it. Your p squared is 3 because you have 3 vectors. Okay. And M22, the space of 2 by 2 matrices. none of these can be obtained as a sum of multiples of the other three. So that C1V1 plus C2V2 plus C3V3 plus C4V4 equals 0. C1, C2, C3, and C4 would all have to be 0. Of course, that's your official test for linear independence. It's related to a lot of other things, like none of these is a linear combination of the others. Okay? But it comes down to C1V1 plus C2V2, etc. equals 0 if and only if all your C's are 0. Well, that's easy to prove. You just write it down. C1 times this plus C2 times this plus C3 times this plus C4 times this. Let's write that down. Assuming this is V1, V2, V3, and V4. Equals 0. What's C1, V1? C1, 0, 0, 0. What's C2, V2? 0, C2, 0, 0. You have them up, and it's pretty obvious that you're going to get, and if it's not obvious, write it out. You're going to get of course, the 0 vector here has to be a 2 by 2 matrix, which when added to any other 2 by 2 matrix, gives you the same matrix. Okay. Linearly independent. And then the linear combination of these vectors, these matrices, which are vectors right now, not arrows for matrices, but this set, as you've seen, satisfies all the axioms of a vector space. Okay. Well, if I want these three things to add up to the matrix A, B, C, D, it could be any matrix, 2 by 2 matrix. Well, I just do A times this plus B times this plus C times this plus D times this. It gives me the A, B, C, D matrix. So every vector in this vector space is a linear combination. And you'd have to write that out. If you see this and write the other condition out, you're going to see it. Just ask yourself, okay, if I want to get the matrix A, B, C, D as a sum of multiples of these matrices, what multiples do I need? Well, this sum is always C1, C2, C3, C4. Okay. So if this matrix is A, B, C, D, then C1 equals A, C2 equals B, C3 equals C, and C4 equals D. Okay. There it is. Just write down the condition. Of course, you got to understand what the test is and how to write out the equation so you can convince everybody that you understand it. Okay? So that you will understand it, so that you can use these ideas. And it's a whole powerful concept, vector spaces in your career. Okay. Well, those are 3 examples. You have the space of continuous functions, the space of integrable functions, the space of differentiable functions. Okay. You have all those spaces. We could write out equivalent conditions, but since those spaces are typically infinite dimensional, it's a little more complicated. I'm going to bypass that for now. Okay, those are the standardizations. Then your book is going to tell you that. We'll take another peek at the order in which your book tells you things. Okay, all right. Small board. number of linearly independent rows. And this means, of course, you regard each row as a vector. Okay. Okay, in reducing a matrix, has multiples of row vectors. The span of the set of row vectors and I should say adds non-zero rows, add non-zero multiples of row vectors. So the span of the set of row vectors gives some matrix. Okay. So the set of row vectors after reduction is the basis for the space spanned by the original row vectors. Okay. You got these rows. You reduce the rows, you're just adding multiples of rows, and if you get a multiple, you get some rows of zeros. Okay, that's okay. The vectors you have left over still span the same space. So it's an important idea. So, example. Matrix might reduce like this. And there's no way to further reduce it because there's no multiple of this row. It'll undo the echelon nature of this matrix. Okay. I'll just say this. I'll write these as column vectors. distance from the two vectors spans the same space as the original row. Now, if you reduce the matrix you started with, say, it would almost certainly reduce down to the identity. Okay. So the vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1 column would span the space that's spanned by your original vector. Okay. If the determinant had been 0, and of course you only had three columns in the original matrix. But if you had a 3x4 matrix that reduced to this, whatever your original rows were, you take the span of those rows, it's the same as the span of these, and these are linearly independent. Because clearly this thing can't be linear, can't be a multiple of this. Because you can't get 0 or any multiple of this. Okay. Now, so far, I want to talk about all the conditions. These rows are linearly independent, which I abbreviated them. Okay. Linearly independent, they form a basis for the original row space. So the original row space has dimension 2. Okay, now this is going to be very important when we start talking about linear transformations. But right now, we'll understand this. Okay. Now there's also the column space, which is a space spanned by the columns in the matrix. If the matrix reduces to this, well, these vectors here don't span the column space of the original. But think about it, row operations don't affect whether one column is dependent or not. Okay, you've got to think about that just a little bit. But it's true. Okay, this means that the first and second columns of the original matrix span the column space. Okay. Now that's something you have to read about and deal with a little bit. But we want to be sure we cover the main ideas. If you understand row space and understand that one thing about the column space with your book and your problems, your assignment very clearly elucidate. Whether you understand exactly why it's true or not, you need to understand that it's true. Okay. So if the matrix was, well, for purposes of time, I don't want to talk about that. Okay. And that's really, you're going to have 3 assignments this week. And this thing about rank is already in the second of the 3 assignments. I want to be sure we cover these things sufficiently that you can get them Monday through Thursday. And also that then we can kind of probe what you understand and what you don't on Thursday, so we can prepare 2 assignments when we do for Tuesday. Okay. Okay, so anyhow, there you have it. If the matrix was, let me write this down in integration. If the matrix was this, then the first and the third vectors of the original matrix and the column space. The column space is a big deal, and when we start doing the transformation, we'll see a little bit more about how they work. Like you're familiar with the idea of linear regression, right? Best fit line, punch into your calculation data and give you the best fit line. How does it do that? It uses run column spaces and linear algebra. It can also be done by calculus. Okay. So hopefully you see that calculus. It's kind of neat to understand how it works. There's a lot of insight to be gained. And that one example of linear regression, it doesn't even have to be linear regression. Linear regression with a square, whatever, comes out very neatly in linear algebra in a way that really illuminates the structure of vector spaces. So these four basic subspaces and stuff, and I'm not going to get into that. Okay, so there you have. Right. The other thing is, again, these don't span the column space. If you go back to the original matrix, column 1 and column 3 do span the column space. And as you'll see, matrix reduces like this. It's got two linearly independent rows. It'll have just two linearly independent columns, so that the dimension of the column space is the same as the dimension of the row space. And we just looked at the solution of the equation AX equals 0. This tells me that the original matrix only has two linearly independent rows, okay? Which means that there's a one-dimensional set of vectors that map to the 0 vector. Okay. Now, that's all I'm going to say right now. We're going to kind of do that. Okay. So that's the main idea. Those are the main ideas of section 3, but we can build on them a little bit. And let me pause, take a quick look. Set a solution to this X equals 0, the third quiz problem. Okay. Now, if A is invertible, which means it's a square matrix, it's not like that one we just saw, that 3x4 matrix. Okay. But if A is a square matrix and it's determined as 0, then you know that the null space is just a 0 vector. Okay. So reminder. The null space is just consists of a 0 vector. Now, we might go over more detail about why these things are true, but another thing we've got to do is talk about changing basis, which we won't talk about until future. I might mention the situation today, but I don't want to lay too much on it in one class. Okay. And we're kind of covering the major points of the two of the three sections we'll be doing. Okay. Okay, so if A is invertible, the null space is just a 0 vector, and that follows from everything I said much of it. You said it earlier, so I'm just reminding you. Okay. Now, Okay. Terminology here for a second. I'm not sure how to talk about this without talking about a linear transformation from the space of one dimension to the space of another dimension. So I'm just going to say, M, or as an M by M matrix, meaning it's equal to the number of rows in the whole matrix. Okay. Well, the dimension of the row space, I have to take a quick peek at your text notation for row space and null space. But I'll just say words are rank and nullity. For the nullity is the dimension of your null space, and the rank is the dimension of the row space. Okay. So word rank here. Nullity is not the null space, it's the dimension of the null space. Rank is not the row space, it's the dimension of the row space. The number of linearly independent vectors in the row space, the number of linearly independent vectors in the null space. And we might just work an example. Let me just check. I should have looked a little more closely at the notation that your text uses. Okay, I wasn't totally thinking about what I was saying. I'm kind of throwing it in my head as I go. But it adds up to n, not m. Okay, the number of columns. Of course, the number of columns corresponds to the number of vectors that you're doing a linear combination of, and it's pretty obvious. But at the moment, it wasn't obvious to me. Okay, I thought it was my oversight. Okay, so anyhow, the rank plus a nullity is the number of columns. Okay, and you could call that number of columns is n. You want nullity to be n. What they use for nullity? Okay, I want to write r plus something equals n, and I don't want to write out the whole word nullity. But that's what would go there. So I got to look again. Take a quick look. I'm going to pause the actually, I probably don't have a notation for it. Just write out the word nullity. You know, I swear I saw the letter R used here. I'm going to go ahead and for you. Just write rank plus nullity. And which is just what I set up here. Okay. Okay, well, let's see if there's anything else that could possibly hang you up. Of course, we'll be able to talk about this a bit again. Next time, yeah, okay, you got particular solutions and solutions of the homogeneous equation. And we have to talk about that stuff. Okay. So what I want you to take away is I did rank null. What the nullity is a set of, or the null space is a set of solutions to this equation. We'll do an example next time, but it's fairly straightforward. In this case, the null space has dimension 0. You don't have any non-zero vectors in the null space. So with C1 times any vector in the null space is the 0 vector. And we don't have linear combinations of the 0 vectors giving anything to the 0 vector. I think I've given you all the main results. Talked a little bit about where they come from. We'll talk in a little more detail next time. Again, next time we get into how do you represent a vector according to different bases. Like the example I gave you is the problem you started with. How would you write the vector? B1, B2, B3 is a linear combination of those basis vectors. And then how would you represent the vector relative to that basis? Fairly simple idea, but make sure you understand that example. And that's the thing you have to do. Okay.